So I'm going to continue our discussion on Tuesday. I want to continue on, start by the volume integrals. Okay, and I want to do one example on that. Okay. So the topics I'm going to cover today, the first one I start by volume integral. And then I'm going to talk about the fundamental theorem of calculus. Okay. So the fundamental theorem of the calculus okay. So this is the theory that really defines what integral is and what is the relationship between integral and derivative. Okay, so now we work with the del operator, and we talked about the gradient and divergence in curl, and this theory can be expanded to them as well. Okay, so the next topics are the same theory, but for divergence, gradient, and curl. Okay, so fundamental theorem for gradient, fundamental theorem for divergence, fundamental theorem for curl, and hopefully we have time to talk about the curvilinear coordinates, and I'm going to start by spherical coordinates. Okay, so these are the topics I'm going to cover today. First, we start by volume integral. Okay, so if you remember on Tuesday, we talked about integrals in 3 dimensions and 2 dimensions. We talked about the line integral. For line integral, we mentioned that we have a start point, we have end point, and we have a path. And we can integrate any vector over this path. For the surface integral, what we have is a surface. Okay, it could be a patch, could be a straight or anything, could be even a closed surface. And what we can integrate is a vector function over the surface of this, over the surface. Okay, and this is basically the flux. We have a vector field, and we want to see what is the flux going through this surface. For the volume integral, we have a shape. We have a 3-dimensional shape, and we are integrating a function over the volume. Imagine, let's say, inside a sphere, inside a cube, or something like that. Okay, so definition of the volume integral. So if you are in 3-dimensional space, it's a triple integral. Okay, so basically, if we have a scalar function like this, we can integrate it t dot d tau. The tau is infinitesimal volume. Okay. So if we are working in Cartesian coordinates x, y, z, then the tau is simply dx, dy, dz. Okay. So looking at this, it's clear that this integral is technically a volume integral of a triple integral. Okay. So basically, you can define it as 3 integrals dx, dy, dz. Okay. Another discussion we had was what defines the shape, right? So if you have integral like this, what defines the shape is the limits that you put on the integral. Okay. So a very simple case, if for x, y, z, if for all of them we say the limits are between 0 to 1, okay, then what happens? We are technically defining this integral being carried over a cube with length of 1 at x, y, z, okay? So that means if I put here x equals 0 to 1, y equals 0 to 1, likewise for z going to 0 to 1, then we are technically carrying this integral over a cube, x, y, z, and the limits are 0, which is right at the origin, and this is 1, okay? So we are going over such cube. Okay, so the limits are important, okay? And depending what kind of shape you have, the limits can be tricky as well. Okay, imagine instead of a cube, we want to integrate over a sphere. Okay, then we cannot simply say from 0 to 1. We should define the limits in a way that they stay within a circle. And the definition of that is x2, y2, and z2. If you add them up, that should be r squared. Okay, so a lot of time it's not easy to carry an integral over a sphere in Cartesian coordinates, and we need to move on to a spherical coordinate, and that is what I'm going to discuss later in this course. Okay, but for some other shapes, let's imagine we have a prism. Okay, and that is one of the examples in your textbook. The integral is being carried over x, y, z over prism defined by x limit is 1, y limit is 1, so 1, 1, and this is connected like this. So the projection on the xy axis is technically a triangle, okay? And then it goes to the limit of z up to 3, something like this. Okay, so imagine you want to integrate on a prism like this, okay? So I'm going to do this example so that you really see what kind of limits you should use, okay? But I want your help as well. So here, what should be the limit on z?
0 to 3.
Let me increase the volume. I can't hear you very well. So the limit on z is, the lower limit is?
0 to 3.
0. The top limit is 3, right? So is it dependent on x or y value, or it's just fixed between 0 to 3?
It's fixed.
It's fixed between 0 and 3, independent of x and y. Okay, so that's the easy part, okay? So if I want to do this integral, I'm gonna say z starts from 0 and goes up to 3, no matter what are the y and x values. Sounds good. How about x and y? The limits are between 0 and 1 for sure, right? But if we just set between x from 0 to 1 and y from 0 to 1, then we would have been covering a projection on xy axis like this, right? We don't want this. We want to get rid of this part. So that means there should be some dependence between the x and y limits, so that if, let's say, y value goes to 1, then the x value cannot really increase beyond 0. Something like that, right? How do you implement that?
The y can go from 0 to x.
Y goes from 0 to x or something else? A linear function of x, so in that sense, that's correct. But if you want to stay within this region, what you should do is that y goes from 0 to 1 minus.
Oh, right, yeah.
Okay, something like this. And then for x, you can put it 0 to 1. Okay, so this limit, if you keep x 0 to 1 and keep y from 0 to 1 minus x, that way you can really implement the what's it called? You can implement the limits. Okay. So let me bring the book and really do the exact function from the textbook. Okay, so this is example 1.8 from the textbook. Okay, so I'm going to write it, example 1.8. Okay, and the function being integrated over this prism is x times y times z squared. Okay. So, and these are the limits that we chose. Okay. So now we can look at the orders and decide one order that is easier. Okay. So technically what I want to do is that I want to separate these into 3 integrals. Do the first one and use the result of the first one, use it in the second one, and use it in the third. Okay. So what I would do is something like this. For the z, the limits are fixed. Okay, so I put the z first, and I do from 0 to 3. Okay. For x, limit is also fixed. I do from x equals 0 to 1. Okay. For the y, limit is not fixed, and I go from y equal to 0 times 1 minus x. Okay. So because the limit for y is not fixed and it depends on x, it's better to do it first so that you can use the result of that for the next integral. Okay. So this is the 3 integrals I have. For the t, I just write it whatever is given. So x, y, z2. Okay. And then we have, I'm going to do dy. Okay. And then dx. And then dz. Okay. And now let me put things in brackets so that it's obvious which integral I'm doing first, which one I'm doing second. Okay. So the first integral I want to do is just this. Okay. And if you look at this shape inside the integral, you can imagine x is constant, z is constant, and we are integrating over y with these limits. Okay. So this is now a simple integral. Simple one-dimensional integral. Make sense? Yes? Okay. Okay, so what is the result of this integral? This is x times z squared. Y dy, the integral is 1/2 y squared. The limits are 1 minus x and 0 here. Okay. So this should be multiplied by 1/2 y squared, and that's going to be 1 minus x. Sorry. Looks good? Yes, so this integral becomes this. And now we are integrating this over x. 0 to 1 dx. Okay. And then, of course, again, this is going to be inside the bracket. And once we do it, we should do dz integral d from 0 to 3. Okay. So integral of this one, the second one is, so what we have is that 1/2 and z squared are constant. They can just come out of the integral. 1/2 times z squared. What we have here is 1 minus x squared times x. So that's times integral of 0 to 1. And so let me expand this here. X times 1 minus x squared is x times 1 plus x squared minus 2x. X times all of these, we get x cubed minus 2x squared plus x. Okay, so this is basically the integrand we have, x3 minus 2x2 plus x times dx. Okay, so this integral is not that, everybody sees this part? Yes? Okay, we have 20, okay. So if you can't see, just let me know. From my board, it is within the limits, okay. So this integral is not hard. It's the first term gives 1 over 4x to the power of 4. This one gives me 2 over 3, negative 2 over 3x cubed, and this one gives me 1/2 x squared. Okay. So what we have here at the end with the limits gives us something, some constant times z. Okay. So I don't want to do it and write all the terms, but I want to say that this is just like a constant here. Okay. So let me do it on the top. So the whole thing here is going to be constant. I'm going to call it c. Right? And then if we move forward, what we have, of course, we have one integral here over z going from 0 to 3 as well. Okay. And if this is a constant, at the end, we are integrating over the 1/2 times c, which is this integral, times z squared from the limit from 0 to 3 dz. Okay. And again, this is a simple one-dimensional integral. Okay. So the basic process, look at your integral, make 3 integrals on x, y, and z. Be very, very careful of the limits and choose the limits such that it covers the 3-dimensional shape that you want to integrate over. Okay. Be careful of the limits and then separate all these integrals. Once you separate them, each integral is going to be one-dimensional, relatively simple integral that you can just carry out. Each of them is going to give you some constant times another variable that will be used in the next integral and variable that will be used in the next integral. Okay, so this way you will be carrying 3 integrals, 3 one-dimensional integrals separately, and at the end you're going to come up with the answer. Sounds good? Okay, so I don't want to work out all the details here because it takes time, but I know it's relatively easy for you. So it's a good practice for you to do this integral and this integral on your own. Any question? Clear more or less? Okay, feel free to unmute yourself because I'm not hearing anyone.
It's good.
Okay, nice. So this is covered now. And then if there's no question, I can move on to the fundamental theorem of calculus. And this is a beautiful discussion, okay? This, we start from the very basic idea and definition of how integration and derivative are related to each other. And we expand that discussion over the derivatives that are from the del operator, okay? So starting from the simple one-dimensional derivative, we gotta move on to gradient, divergence, and curve. And here the basic idea is this. We want to relate the integral of a derivative to the boundary values, okay? And that's important in the sense that we use that very, very often in physics. Now, a lot of laws in physics like Gauss in electrostatic or the Ampere law in magnetism, these are in a way an expansion and application of the theorem that I'm going to discuss today in physics, okay? And this is one of those discussions, if you read these, you do a couple of examples, and you really, if you internalize the concept, you will learn that forever, okay? And that's very nice and beautiful discussion, as I said, okay? So let me erase the board and start from the fundamental theorem of calculus. Okay, so if you have one-dimensional function, okay, suppose fx is one-dimensional function of x, and then we have the derivative of x in the format of df over dx, okay, and let's define function capital F like this. Okay, so we have these two things. Okay, if you integrate dfx over dx, if you integrate it over x from, let's say, a to b, okay, what do you get in terms of f of a and f of b?
You get capital F on B minus capital F on A.
Capital F or a small f? Let's do one more step so to make it obvious. Okay, so if you integrate something like this, you're technically integrating dfx from a to b, right? And that is the small f b minus the small f a. Okay. Maybe you have seen in a more familiar form of integrating capital Fx dot dx from a to b, and that being equal to fb minus fa. Again, with the definition that fx is dfx over dx. Okay, so if I want to put it in words, what's happening here is that here we have the integral of a derivative. Okay, so this integral is the integral of a derivative of a function. Okay, so I just write it down and I'm going to repeat this over and over for our discussion today. So we have here the integral of a derivative. And what we have on the right-hand side is the value of the function on the boundary. Okay, so the right-hand side is only dependent on value of f on b and value of f. Okay, so this is the value on the boundary. Okay, so if you integrate a derivative of this function, the whole integral at the end depends on the value on the boundary. Okay, so this, I suppose, is very, very familiar to you. This is what you have seen in calculus probably over and over again. Okay, so I wanted to stick to this concept, and I want to expand it and use it for gradient, divergence, and curve. They have different shapes, but again, the concept is relatively the same. Okay, so any question on this? I want everyone to be very comfortable with this discussion so far. Okay, looks like everybody is happy. Okay, so now I'm gonna discuss it in terms of the gradients. Okay, so I want to construct something like this, but based off the gradient. Okay, but before that, let's look at some geometrical interpretation of this. Okay, let's see what we have here, and let's see what it means integral of the derivative. What the integral of the derivative means. If you look at this function on a graph like this, let's say here we have fx, this is a, and this is b, and imagine from a to b the function takes a path like this. Okay, so of course this is fa, and then here we have fb. Okay, so the integral of the derivative means we are chopping the path from a to b to a small pieces. Okay, and once we do derivative is a slope. Okay, So fx times dx basically means we have this part with the length of dx over x-axis, and we are multiplying a slope by dx. Okay, if you multiply a slope by dx, what you will be getting is this infinitesimal change over y-axis. Okay, that means if you move this small step here, and that is the direction that we are integrating, on the y-axis, the result of integral is going to increase this much. Okay, and imagine you are integrating from A all the way to B, and that means the integral outcome is going to show you an increase from, on the y-axis, from A all the way to B. Okay, and if you move from A all the way to B, the distance it's covering is going to be FB minus FA. Okay, so the integral of the derivative pretty much reflects how much you're going to move on the y-axis. Okay, and the limits define how much they move, and at the end, the outcome only depends on the values on the boundary. It means FB and FA, independent of what's going on inside and what rate is increasing over your integration interval. Make sense? Is it making it more clear? Okay, okay. So now let's move on to the gradient. So to do that, I'm gonna actually erase pretty much everything and start from the basics. Okay, so now imagine you have a scalar function of three variables, x, y, z. Okay, and then we take gradient of t. Okay, and it's a three-dimensional function. If we move very small step, infinitesimal step, the L, if we multiply the gradient by dot product times the L, what we get is dt, various infinitesimal change in t. Okay, if I want to expand what I have, it's going to make probably more sense, and that is dt equals to, in terms of the vector notation, this is a dot product, so the x component of the gradient should be multiplied by x component of the L. So the L is basically, if we are in Cartesian coordinate, it's going to be dx, x hat, plus dy, y hat, plus dz, z hat. Okay.
Professor, is this the fundamental theorem for gradient, right?
This is the fundamental theorem for gradient, yes.
Thank you.
So this is we covered, and we are on the third one. Okay. So we have this dl, and then the gradient of t is dt over dx times x hat plus dt over dy times y hat plus dt over dz times z hat. Okay, and the dot product of these is going to be dt over dx times dx plus partial t over partial x dy, sorry, this is y, plus partial t over partial z dz. Okay, and now what is dl? Like physically, what does it mean? dl means something like this. If you are on a coordinate like this, you have, imagine you have the starting point A, right? And you have an end point like B. Okay, so if you are moving from A to B with the smallest steps, each smallest step is something like dl. Okay, so you can imagine we have this dt and we are integrating this from A to B. Okay, and the way I want to write that is integral of from A to B gradient of the t dot dl. Okay, so if I write that, pretty much I'm integrating the gradient of the t from A all the way to B. Okay, and at each step, the smallest step, the move I'm making here is df. Okay, how much the value of the t is changing from this point to this point, okay, that change is dt. Sounds good? So basically this integral is the same as integral over dt from A to B. Okay, so if you are making all these small dt changes from beginning to the end, what's happening is that at the end, the result of this integral should be tb minus ta. Okay, so again, what we have here, we are integrating a derivative. Okay, so this is the integral of the derivative, and then what we have on this side is the values on the boundary. Sounds good? So integral of the derivative and the values on the boundary what we have. Okay, so in a way, this is very similar to the one-dimensional case. We integrated a derivative. The only difference is that the derivative here is in the form of gradients. Okay, and this is quite interesting from one perspective. Do you remember on Tuesday, we talked about the line integrals, and something I mentioned is that if you do a line integral, okay, of a function from A to B, that depends on the starting point and end points, as well as depends on the path. Okay, so if you take the random vector function like f and integrate that over this lens, okay, over this path, it is going to be dependent on the path. Okay, and if you remember, I also said there are very special set of functions that if you integrate, at the end, it's going to be independent of the path you are taking. Okay, so this gradient is in a way defining those set of functions. If a vector function can be written in terms of the gradient of a scalar function, okay, listen, if a vector function can be written in terms of the gradient of the scalar function, then that vector function, if you integrate that over the line, the result of the integral is independent of the path, okay? And that's what happens for conservative field forces, okay? Conservative forces, if you integrate work, at the end does not depend on the path, depends on the beginning and the end. Okay, so the mathematical basis of that is this. The vector can be written in terms of the gradient of a scalar function. And that happens for electrostatic field as well. Okay, electrostatic fields are electric field. Electric field can be written in terms of the gradient of the potential. And because of that, any integral, any line integral at the end depends only on the boundary condition. Okay. So this is in a way special, that the line integral only depends on the boundary value. And that is in a way a characteristic of the gradient. Sounds good? Okay. And one more interesting thing. So here I mentioned going from A to B. Okay, so we are moving from A to B from one point to another point. What if you make the integral over a closed loop, starting from A, going all the way, far away, and coming back to A again? What is the result of the integral? Look
Should
it
be
zero?
0, right?
Starting from A, coming back to A, it becomes 0. Okay, so for any loop, if you're coming back, whether it's a small or large, okay, you can imagine you are going so far away and then coming back. If you do this integral, the value somehow it cancels out itself and becomes 0. Okay, and that is again can be related to the work done by conservative forces. you can move one object, okay, so far and bring it back again, the work done by conservative force is going to be 0. Okay, it's like a gravitational work. I throw this marker so high up, but once it comes back again, the work done by gravity at the end is 0. Whatever it did over going up, it's going to cancel that when it's moving down. Okay, the same thing with electric field. Okay, magnetic field, no, it does not have this characteristic. Okay, magnetic field, we integrate that over a closed loop, and that's actually a value. And from that integral, we can calculate what the strength should be. That's Ampere's law. Okay, we will discuss this later, probably in the second chapter of the book. So magnetic field can never be written in terms of the gradient of a function, of a scalar function. Okay, any question? No? Is it more or less clear for everyone? If it's not, it's time to ask question.
Yep, it's clear.
Okay, good. All right, so let me see, there anything specific about this? Pretty much this. Okay, and then I want to move on to the divergence and then curve. So we covered this one too. Okay, so expanding that for the divergence, we need to start first by supposing we have the vector function of v, which is function of x, y, and z. Okay, so this is a three-dimensional vector function, and the divergence of v basically gives me a scalar function. Okay, so divergence of v gives me a scalar function. And now let's imagine we have a volume like this. Okay, it could be a sphere, could be cube, or it could be any random three-dimensional shape, x, y, and z. And imagine we integrate the divergence over the volume of this shape. Okay, so divergence of v times d theta. Okay, so d theta again is gonna be like dx times dy dz if you are working in Cartesian coordinates. Okay, so we get this one, and this function is actually equal to the integral of v times dA. The first integral is on the volume, okay? So it covers all the volume inside your shape. The second integral, v dot dA, is integral on the surface. Okay, so I write S here, okay? And this is integral of the vector function over the area, okay? So in a way, this integral is the flux that passes through the membrane of this shape. Okay, and the first function is the integral of the divergence over the volume. Okay, so the way you can think about this is this. Imagine from this volume, I take an infinitesimal space volume here. Okay, so this is the tau, which is dx, dy, dz. If you look at the divergence in this small volume, divergence of v times d tau is going to tell us what is the flux going out or inside of this very small space. Okay, and once we integrate this divergence over the whole space, okay, now you should imagine we have this small cube here. The whole shape is made of many, many small cubes. Okay, So whatever flux is going out of this side, okay, is technically entering another cube, which is right on top of this, okay? So the flux going out of the bottom one is entering the flux, into the top one, okay? So if you add up the divergence, okay, if you integrate this divergence, all these small fluxes going through the surface, they cancel out each other. For one of them is positive, for the other one becomes negative. If for this one is negative, for the other one becomes positive. So if you integrate over the whole volume, everything cancels out each other. There is no flux, net flux going through this, except once you reach the boundary, okay? Once you reach the boundary, that's where the flux is either going out or coming in, and it doesn't cancel out with the neighboring cube, okay? So you make this integral, everything cancels out except the surface integral of the flux of the vector function v over dA. And dA here is the area right on the surface of this. Okay, so this is like 1 dA. And we are integrating over the whole surface of this three-dimensional shape. Okay, so this is like adding fluxes of small cubes, which becomes the flux going through the whole shape. Okay, but if you look at this, again, this is a derivative, and the whole thing here is the integral of the derivative. And what we have is actually the value of the function right on the boundary, okay? The right-hand side integral, this integral does not depend on what happens to the value of vector function v inside the shape. It only depends on the boundary, okay? So this is basically the value on the boundary, okay? And this rule, this divergence rule, is again very popular in physics. This is exactly the way we calculate electric field, okay, from a charge distribution. In electrostatics, we will see that the divergence of electric field is proportional to the charge distribution, okay, in the space. So if you integrate electric field over the surface of this volume, that integral should be equal to the integral of the electric charge inside that volume, okay? I'm sure you have done that in like physics 226, that you want to calculate the electric field. What you do is that you look at the integral on the surface and relate that to the total charge, okay? Total charge means integral of the charge over the volume, okay? And what was the name of that rule? Gauss? Yes, yes, that's the Gauss rule, okay. So this is in a way the fundamental theorem for divergence. This is very famous, and this is more known as the Gauss theorem. Okay. Any question on this?
Yeah, I have a question.
Sure.
So what you're saying is that with each infinitesimal volume, their fluxes cancel until they reach the boundary of the volume?
Yes. The neighboring infinitesimal volume, if you look at the flux of them and add them up, okay, they just cancel out the flux that is going through the boundary. Because if it's positive flux, let's say coming out of the first one, the bottom one going to the top, the same flux, if it's positive from here for this one, becomes negative. So if you add them up, they just cancel out each other, okay? All the way until they reach the bond, they reach a boundary, okay? Then at that point, they are not canceling out each other anymore. Does it make sense, like the geometrical intuition? I really want to have intuition about these things.
Yeah,
Then you really feel it by your heart.
I just
see the beauty of it.
Yeah, I wanted to make sure that visually I understood what was going on.
Good. Okay. Very good. And by the way, your textbook it's very nice textbook. Okay, in the way that it has a lot of explanation and simple explanations. Okay. You know, some physics textbooks are excellent, but very dense. Okay, those textbooks you cannot sit on your own and read it. You really need someone to explain it step by step. But this textbook by Griffiths is amazing in a way that probably if you read the book, it has a lot better explanation than what I do right here, okay? So please take your time, read the book line by line, and then you will have a better vision of all the discussions we have here. Of course, whatever I teach here is from the book, okay? There's gonna be like, hopefully 100% overlap, but reading the book on your own gives you another view of the topic as well. So very strongly, I encourage you to do that. I don't know you haven't been doing or not, but hopefully you do it. Sounds good. Any more question on this? No? Let me take a look. Okay, so I'm going to move on to fundamental theorem for curl. Let me get rid of this. All right, so for the curl, again, suppose we have the function v, which is a vector function of x, y, and z, and then we're gonna look at the curl of v, okay? So what was the conceptual definition of curl? What does it reflect? So divergence was about the fields that are diverging or converging, okay? So the first thing about the divergent that comes to my mind is a function that looks like this. Okay, so when I think about divergence, this is the first thing that comes to my mind. How about curl? What kind of shape does it portray for you?
Like the swirl of a vector
Swirl
field
of the
around a
vector
point.
around one point. Okay, so this is pretty much the curl. Could be like this, function going like this, or function going like this. This is also curl. Okay, so if a vector function has a positive or negative curl, that means it's swirling around one axis, one point, or many points. Okay, so this is curl. Okay, so now imagine we have a surface, we have a patch like this, a random surface, doesn't need to be flat or anything. Okay, so what we can do for the curl is that we can integrate the curl over dA, over the surface of this, okay? And that means so dA is gonna be very small area here. Okay, so this is the A. And if we integrate it, we are technically going over the whole surface here, okay? And adding the contribution from the curl of each of these small things. And imagine if you have a curl here, okay, like this. So each infinitesimal area has a curl into it, okay? Very similar to our discussion on the divergence. If we add up the curl of all these neighboring infinitesimal area, what's happening is that right at the boundary, the curl of each of them is canceling the other one, okay? So the left one cancels the curl because the way the field is going for one of them, let's say this is a boundary, for one of them it's going this way, for the other one it's coming the other way, okay? So if you add two neighboring patches, okay, the curl cancels out here. The same thing happens for the other boundaries. So if you integrate over the whole surface of the boundary, all these curl contributions cancel out each other. except right at the boundary where the patch is ending, okay? So if you do that, this integral over the area is going to be equal to the integral of v dot dl. Okay, so here we have curve, here we have the area, okay, and here we have the value of the function over the boundary. Okay, so this is on the surface and this is on the loop. Okay, this is two-dimensional integral. This is technically one-dimensional. This is a line integral. This is surface integral. Okay, so again, this is the integral of the derivative of the derivative. In this case, derivative has the form of curl, and this right-hand side depends on the value on the boundary. Okay, and the boundary here is a line that is defining this patch. Okay, so now I draw this patch and one surface here. The point is that if you have a loop, the surface that connects that loop is not unique. Okay, so this is one way, connecting everything directly. Or I could define a surface like curved surface like this. Okay, imagine the surface is rubber and you just expand it from the other side. Okay, something like this. Okay, so it could be a completely different surface, much bigger surface. Okay, the interesting thing about curl is that if you can write a vector function in terms of curl of another function, it doesn't matter how big the area is. Okay, as long as it's from one loop, from the same loop, the integral of the curl is going to be always equal to the line integral of the function over that loop. Okay, so you can have a small loop, okay, but very big area, okay, and imagine you can expand that, okay, you can make infinite number of choices for the area that covers this loop, okay. For any area, if you do the integral, the result of that integral is going to be the same and equal to the line integral of the function over the loop, okay. And this is something that we use in magnetism, okay. If you integrate magnetic field over an area or patch like this, the result of that is going to be equal to the line integral of the magnetic field over this loop. Okay, no matter how big the area was. As long as the loop is defined, you get the answer, okay? And the reason we can do that is that we can write the magnetic field in terms of the curl of another field. Okay, we can write it in terms of the curl of another field, and that's enough for us to conclude any area you can choose, big or small, and the result is at the end only dependent on the loop that defines that area. Sounds good? A lot of discussions? Okay. Any question on this? Okay. And now you can imagine if we have a closed surface, okay? Let's imagine we calculate this curl over a sphere, which is a closed surface, or we integrate this over a cube, okay, closed surface. The line integral of the boundary, there is no open boundary here, it's closed. So if you go on a surface, closed surface, this integral just becomes zero. Very similar way that the gradient, if you integrate that over a closed loop, that's always zero because there's the boundary integral is zero. Cool? Any question? No? Everyone's happy?
As a clam.
Good, okay. So I'm done with the discussion on the fundamental theorems, okay, and I want to start talking about the spherical coordinates. I don't think I'm going to finish that. We only have 15 minutes, but I'm going to start that and continue that on Tuesday. Okay, so let me raise this. Okay, So let me start by asking the basic question of how many variables you need to locate a point in three-dimensional space. Let's
3.
start by two-dimensional space. How many variables do you need?
3.
If you're in two-dimension,
Oh, 2. 2.
you need two variables, okay? So if you want to locate any point, okay, you need two variables. In Cartesian coordinate, it's x and y, okay? But we are free to choose other coordinates as well, okay? We can, a very popular coordinate is polar coordinate, okay, or spherical coordinate. We have cylindrical coordinate as well, okay? If you move to three-dimension, you need three variables, okay? If you move to n dimension, you need n variables to locate your point, okay? So a spherical coordinate is something that makes it a lot easier for us to do integration and a lot of calculus and vector calculus if the shape we are dealing with has either spherical symmetry or even if it doesn't have a spherical symmetry, we are dealing with boundaries that are on a sphere, okay? So the basic definition of the spherical coordinate is like this. Now imagine you have this coordinate system, okay? We have x, y, z. Okay, so I'm starting by the Cartesian coordinate, and now imagine you have one point P here, okay? So of course, one way is assigning an x, y, z component to this P. Okay, that's one way. But now I want to use a different one. I want to get rid of this and choose a different set of variables that define that locates my point P. Okay. And what I do is this. I connect P to the origin. Okay. And the first thing I look at is how far I am from the origin. Okay. And that's going to be my first variable, R. Okay. That shows the distance of P to the origin. Okay. And the second thing I look at is the angle that the line here makes with the z-axis. Okay, and I'm going to call that theta. Okay, and that is a polar angle. So instead of x, y, and z, I'm using r, which is radial components, and theta, which is a polar angle. Okay, is this enough for me to locate the point P? It's not enough. Okay, we can imagine if I rotate theta and r aligned around the z-axis, there's going to be many points with the same r and same theta. Okay, so another component which is important is what angle P is making with x and y axis. Okay, and the way to formulate that is this. I look at the P and I look at the projection of the P on the xy plane, okay? So if I want to draw this, I get this, and parallel to this, I get something like this, okay? So this point is projection of the P on the xy plane, okay? And what I do is that I connect it to the origin. So this line is confined on the xy plane and is technically the projection of the R on the xy plane, okay? And what I look at here now is the angle that it makes with the positive x-axis. And I call this phi, okay? So R, theta, and phi. The radial components, the polar angle, and the phi is azimuthal angle, okay? So with these three set of variables, I can locate any point in three-dimensional space, okay? So x, y, z, and now I'm gonna use r, theta, and phi, and this is the basic definition of a spherical coordinate, okay? So now we have this set, which is nice if we are working with spheres or any problem with any spherical symmetry, okay? Now, if you remember, we have been doing a lot of calculations using unit vectors, Okay, so the next step is defining unit vectors in the new coordinate. Okay, that becomes a little tricky, okay, because we don't have something like x, y, and z. We have r, theta, and phi. How do you define the unit vector for theta or for phi? Okay, so now let's look at that. If you have unit vector, you really want to define the unit vector in the direction that your variable that shows the increasing variable. Okay, so that means if you have r in this direction, okay, it's nice to define the unit vector r along the same length. Okay, and I'm going to call that r hat. In a way that if r increases a little bit, the point P moves in the direction of r hat. Okay, so that is the basic idea we want to use to define unit vectors. If you increase r, you want to look at the direction of the motion of P, and that should be in the direction of r hat. Okay, so r hat becomes a vector along the direction that connects origin to the point P. The size of r hat, 1. Very similar way that we define the size of x hat, y hat, and z hat. Okay, so r is a unit vector in this direction. How do you think about theta and phi? Okay, let's look at the theta first. Okay, I want to choose the direction of a unit vector in a way that if I increase theta, my point P moves in the direction of theta hat. Okay, so now think about this. You keep r constant, you keep phi constant, and you increase theta a little bit. What direction the point P is moving? This way? That way? It's moving down this way. Okay, so this is the direction it's going to move. Okay, so I define theta hat, a unit vector in this direction. Okay, and by this direction, I mean this should be perpendicular to r. Okay, and that's the direction that we can find by increasing theta a little bit, and this is theta. The size, the magnitude is still 1. Okay, the same as r hat, x, y, z hat, and everything else. Okay, so this is the theta hat. And now think about phi. If you increase phi a little bit, what direction the P is moving? That direction is technically in the same plane as x, y. Okay, so it's going to be a direction that is going to be at the end parallel to the xy plane. Okay, so let's first show that in this plane. If we increase theta a little bit, okay, we are extending the position in this direction. Okay, is it a good noise? Let's move it a little bit this way. Okay, and this is phi hat. Okay, this is a vector in xy plane. If I want to show it up here, I can use the same vector up here. So it's going to be almost like this. And this is phi hat. This is P and this is phi hat. Okay. Sounds good? So here I define the unit vectors. So now these unit vectors have also the nice characteristic that they are orthogonal to each other, okay? R is orthogonal to theta, phi hat is orthogonal to both of them, okay? So we have a set of orthogonal unit vectors, and that is important because that allows us to write any vector, okay, like A, in terms of 3 components, the r hat, theta hat, and phi hat components. So it's going to be the r component, there's going to be a theta component, and there's going to be a phi component. Okay, we can write any vector in this format because r, theta, and phi are a set of orthogonal functions. Okay, so far so good? I see 2 chat messages here. Josh, is R pointing outward the board? R is not directly outside the board. It depends on where P is, but it could be outside if I bring P all the way here, okay? Or it could be parallel to the board. If I move it further away, that means if I increase theta. So per se, I cannot say R is outside the board. R hat is in the direction of R. Okay, so it could be like this. If this is R, then R hat is this little marker here. Okay, and if I change theta, I'm changing this direction. Okay, so that's pretty much how R hat and R are related. Make sense? Okay. If I had 3 hands, I could really show the whole coordinate system. I have only 2. Cool? Okay, so I'm going to stop the discussion here, and I'm going to give you just one more piece of information that shows a little bit of complexity with the spherical coordinate. In Cartesian coordinate, x hat, y hat, and z hat are always a constant, okay? The direction is constant, the size is constant, everything is a constant. For the polar coordinate, depending on what point you have here, the direction of r hat, theta, and phi hat changes. Okay, so they are, in terms of the magnitude, yes, they are constant. The magnitude is 1, but the direction depends on p. Okay, so direction depends on where the point is, and once you're doing the integration and things like that, you cannot always consider theta hat, r hat, and phi hat, these unit vector, as a constant because you're variable. Size is constant, direction is changing. And a lot of times the problems that we are dealing with the spherical coordinates, the geometry is kind of makes it clear for us to how to deal with these unit vectors and so on, okay? So later on Tuesday, what I want to do is that I want to define the del operator, gradient, divergence, and curl in polar coordinates. You will see that definition of these things change a little bit. I mean, the conceptual definition is the same, but mathematical format of the del operator is going to be a bit different, okay? And then I'm going to do 1 or 2 examples that we're going to work with the spheres and measure volumes and so on, so that you see how this polar coordinate, spherical coordinate, makes certain things very easy for us. Okay? Any question?
No.
Okay. So it's end of the class. I want to finish my note on Critic. I talked to this company, Critic. What they said is that they cannot easily increase the file size limit because they said it's going to make the whole process slow, okay? But they suggested that everyone is now using the third-party cloud, like Dropbox or YouTube, okay? So next week, I'm going to do a test, and we're going to decide on either use Dropbox or YouTube. You upload from your phone to YouTube and share the link and submit the link to the Critic for your quizzes, okay? And I hope that's easy. Usually on the phone, you can make a direct YouTube upload, okay? So that makes the upload process easier for you, hopefully. And then you just need to get a shareable link from YouTube account. And the same way that I share these videos to you guys, you can submit a small text file that has only one YouTube link and do that, okay? So I looked at the quizzes you guys submitted last time, and I looked at the feedback and evaluations. You did a really good job, okay? A few students did not submit anything. I really want you to the next practice, please do submit and please provide the feedback, okay? The reason is this, it's more important to contribute in this type of peer review than regular quiz, because if you don't do a regular quiz, then you just miss something, miss some submission. But here, if you miss submitting, okay, what happens is that your submission becomes also a task for your peers because they want to evaluate 5 quizzes, okay? And then you want to evaluate other quizzes as well. So if you miss submission, you're gonna miss 3 different parts as well, okay? And you're making your peers miss evaluating your quiz as well, okay? So I really want everyone, please participate in the next test we do next week. And so basically, I want you to try uploading to YouTube and sharing the link. Sounds good? Any question?
No, Professor.
Good. Okay. So I let you go. Enjoy the rest of your day, and I will see you on Tuesday morning.
Thank you, Professor.
Thank you, Professor.
Bye.
Good day, Professor.